This is a bit of a meaty boy in integral transform methods, so let's get into it. We're first going to define the complex plane, and so that's pretty simple. It's basically taking this and just calling it a function of z. Z is x plus iy, which is the real and imaginary plane or a complex plane, so it breaks that apart. Got a separate video on that, so I'm not going to go over it entirely, but you know that you should break it up. So it's just basically replacing the x's with 1 plus z squared. So we want to integrate f of z over the real line, and we will use the residue theorem with a semicircle contour in the upper half plane. So let's first identify the singularities and rewrite the denominator. So 1 plus z squared would equal z minus I, z plus I. You should know I squared equals minus 1, so nice and easy substitution. So now we will have this as fz, which equals 1 over z minus I, z plus I, all squared. The function has second order poles, i.e. double poles, at z equals I and z equals minus I. And since we're using a contour in the upper half plane, only z equals I lies within the contour. I might as well just draw a quick explanation of that. So this is kind of what we're looking at. Pretend that this is symmetrical. So you've got minus I here, and let's say you've got I here, and you've got minus R. This is, here is RE. Can't really fit it in, but RE is here. And then you've got here a gamma, and here you have the gamma R, and then this is the imaginary plane. So this contour, this semicircle, doesn't include minus I, so we can almost ignore it. We're looking at the singularity that falls only here. So we're only going to compute at z equals I, and we will need to use the residue of fz at the double pole of z equals I. So for a second order pole, the residue is given by the residue here of fi, because we want z equals I. I'm just going to write this here, z equals I. That's all we care about, which equals the limit when z goes to I for d dz z minus I squared, let's put some brackets here, of fz. So you will now get z minus I squared fz, which equals z minus I squared over all of that. So you're going to have z minus I, z plus I, all squared, which equals z plus I squared. So now we're going to differentiate this. So I'll put, to save me writing it all out again, pretend we're going to, this differentiated is going to equal d dz. Pretty simple. This is just going to be a chain rule. So if you let t equal all of this, it's going to be t to the minus 2. Substitute out. So it's going to be z plus I to the minus t, which is minus 2 z plus I minus 3. Okay, we're almost there. Let's now evaluate z equals I. So we've got this here. So we're going to get minus 2, substitute in I for here. I plus I equals minus 3. That's going to be minus 2, 1 over 8i cubed. So we know that I cubed equals minus I. So minus 2, 1 over 8 minus I is going to be 1 over 4i. So we now use the residue theorem. The contour CR at the semicircle of radius r in the upper half plane plus the real axis of r to r. So, sorry, minus r to r. So that's going to be CR of fz dz, which is going to be 2 pi I multiplied by the residue, what we just calculated, of fi. So all you're going to do is what you've calculated here is multiply it by 2 pi I. So you're going to get 2 pi I times 1 over 4i, which equals pi over 2. We now show that the semicircle arc vanishes at r to infinity. So this is just a little quick proof. It's going to be z, so the magnitude of fz is going to be the magnitude of 1 plus z squared, which is going to be less than or equal to the magnitude of z squared minus 1 all squared, because it goes to 0, as the magnitude of z goes to infinity. So the integral for, I'm just going to write I, don't want to write that all out again, equals pi over 2. Not really that straightforward, bit nasty, bit horrible, but that's integral transform methods for you.